Hi students. So today we start optimization tutorial 6. Today we are going to look at examples on direct search methods. I am Dr. Ganguly. Now in this tutorial today we are going to look at concepts such as the direct search method itself, what is the search direction, what is line search or 1D search, what is the descent condition and what is the line search criteria. And this particular tutorial goes with optimization lecture 6 on direct search. So if you haven't looked at that particular video, make sure that you take a look at it. And also if you are interested in the full course, take a look at the optimization playlist for the full course. Now let's start with the problem, and we are going to slowly build up the concepts which are there in lecture 6. So the first question is, the starting design of an optimization algorithm is given as x0 is 1, 2. So this is a vector. There are two design variables here. Now the change in the design variables in each of the following iterations is delta x0, delta x1, delta x2. And then the question is to calculate x1, x2 and x3. So here we are being asked to use a very important and fundamental equation in direct search, which we are going to discuss next. So this is the equation xk plus 1 is xk plus delta xk. And this simple equation actually encompasses all the direct search algorithms out there in optimization. And what happens is that you are at some point xk, you go to the next point xk plus 1, and this step you take, the delta xk, this is actually something which has to be calculated by the algorithm. And you will see that there are different methods about how this can be calculated, but the fundamental premise of these algorithms is essentially dictated by this very simple rule. So let us start with what has been given to us, which is x0 and delta x0. So again here 0 refers to the starting point of the algorithm. So x1 will be given by x0 plus delta x0. So I substitute k is 0 here, and so I get this particular step. And immediately I take x0, 1, 2, I add the delta x0 component here, 0 0.2 and zero point 0.3, and I get the next value of the design variable, which is 1.2 and 2.3. Now I continue this process, so I take x2 is x1 plus delta x1 and I add x1 which has been obtained in the previous problem, and I add delta x1 which has been given in the question before, and so I get the solution 1.3 and 2.5. I continue this process to x3, which will be x2 plus delta x2, and so I get this 1.3 and 2.5 from here, and then I add the delta x2 term here, so I get this 0.05 and 0.01, and the solution becomes x3 is 1.35 and 2.51. So you can see this is how the typical direct search methods proceed through the design space. They move through the design space essentially searching for the optimal point. Now let us come to a more realistic question, and this question is something we are going to use throughout this particular lecture. So we are going to have the starting point as 1 and 2, and we are going to have a search direction given by the algorithm dk is minus ck. This particular algorithm, known as the steepest descent method, is something which is very popular, very fundamental, and we are going to use this method in this particular lecture to demonstrate the search directions and so on. Now there are many different methods out there, so this is simply one method, and the one dimensional step size is given by alpha k, and the question is to calculate xk plus 1 and f alpha k for the function fx is x1 square plus 2x2 square. So this is a function of two variables, therefore you have the design variable or design vector given as 1 or 2, two variables which are given at the point xk. So let us now take this particular problem and see how we can move forward with k. So I have written in red whatever was specified to me in the problem, that is xk was 1, 2, dk is minus ck, and of course f of x is x1 square plus 2x2 square. Now remember that dk is minus 6k simply means that this ck is the gradient, and so I'm taking the search direction as the negative of the gradient. Now in optimization, what happens is that we take this delta xk and we write it as alpha k into dk. So we split this delta xk into two parts. The alpha k part is known as a one dimensional value which we are going to obtain. This is something which is obtained by line search or one dimensional search, and the dk, which is a vector, is actually the search direction. So different algorithms are going to give you different search directions. So in the steepest descent method, the search direction is simply the negative of the gradient vector. So let's calculate the gradient vector of this function. So we know df by dx1 is 2x1, df by dx2 is 4x2. So the gradient vector is 2x1 and 4x2. So again, it is a two-dimensional vector. So I can immediately get dk is minus ck. So that's going to be minus 2 into 1 minus 4 into 2. So remember that all these values such as d, c have to be calculated at the current point at which you are at. So in this case, you are at point xk, which is given by 1, 2. So we substituted here 1 and 2 for x1 and x2. And so we got the dk vector as minus 2 and minus 8. So now I use the general formula here, and I can write xk plus 1 is xk plus alpha k into dk. dk is from here, the xk value is from here, and the alpha k is a value which we are going to simply write down as alpha k here. So this is the value for xk plus 1. So you can see that once I have the value for xk and I have the value for dk, I can write xk plus 1 simply in terms of alpha k. Now what I can do is I can go to the function f of x, which is here, and I can find out what is the value of f x k plus 1. So I'm going to substitute these two values in green for xk plus 1 into x1 and x2 here. So I get this equation here. So what I've done is I've substituted the x1 value here, that becomes squared, and I've substituted the x2 value here, that also becomes squared. So this particular expression is nothing but the expression here, that is fx is x1 square plus 2x2 square, and the points x1 and x2 are what is there at k plus 1th point. So with this I can realize that now I have converted this problem into a one-dimensional problem. So essentially I can write this f x k plus 1 as simply f alpha k, because this function on the right hand side is only dependent on alpha k. So this last function in green, that is f of alpha k, this is the problem which we have to solve in one-dimensional search, for example. So this is often known as the 1D problem. Sometimes the line search is used to find the minimum for that. But let's try to slightly simplify this problem. So what I have done is I have dropped the k value, and that is often done because we know at a current point that we are at a particular iteration k. So what we can do is that we can simply write this as alpha, and so this is the function here. I expand these two squares out, so I get these terms here, and then I do some further simplification. So I multiply this part by 2, I get this here, and then I add, for example, 8 plus 1 gives me 9, then I have 64 and 4, this gives me 68, and I have 128 and 4, and that gives me 132. So I obtain this nice looking quadratic equation in green as the 1D problem corresponding to the iteration k which we need to solve. So let's try to do that next. So before we do that, there are certain characteristics of the problem when you look at search methods, which we are going to all look at in terms of example. We demonstrated many of these issues in the lecture class, that is lecture 6, and now let us look at the example. So again the same problem, xk is 1 2, dk is minus ck, and function is fx is x1 square plus 2x2 square, and we have to show that f xk is f alpha k equal to 0. So let's try to do that. So again we know xk is 1 2, fx is x1 square plus 2x2 square, And so I can write fxk as x1 square plus 2x2 square, and xk is 1, 2. So I put those values here. x1 is 1, x2 is 2, and so I get here 1 plus 2 into 4, which gives me 9. Now if I were to take the function I obtained in the previous question, or the solution of the previous question, the alpha function that is given by this equation in blue, and if I set alpha equal to 0, you can see I immediately get the value of 9 here. And so I can say that fxk is f at alpha k equal to 0. So essentially this is what is meant by the one-dimensional search. When the value of the step size is 0, then you are at point xk, and at the point where this alpha k is a point corresponding to the minimum of the function, we are going to get xk plus 1. So let us try to do some more calculations here. Again, exactly the same problem. So we have xk is 1, 2, we have dk is minus ck, and now the question is to find the optimal step size here, alpha star, for the same function x1 square plus 2x2 square. We also need to calculate xk plus 1, fxk plus 1, and the value of the function at this alpha star. So let us first try to get the value of the line search, or the optimal step size. So again, the function was obtained previously in the last question, and then what I simply have to do to find the minimum point of this function is I have to take f dash and set it to 0. So that's what we have done here, and then I can solve for alpha star, and that gives me 0.25757, or 17 by 66. So this is the best possible value of the step size here, the optimal step size. And if I move this much along the search direction, then I am certainly going to get a good result for xk plus 1. So let's try to do that. We take this particular step size which we have obtained, 0.25757, and we have the formula for xk plus 1 is xk plus alpha k dk. We substitute these values here. So xk is 1, 2, alpha k is 0.25757, and dk is minus 2 minus 8. So with that I get this particular solution here. So I get xk plus 1 in terms of two variables here. X1 is 0.48486 and x2 is minus 0.06058. Now let us substitute these two numbers in the function fx, which is x1 square plus 2x2 square. You can see here x1 has been substituted here, x2 is here, and so I get 0.2424. So this is the value of the function at the next point. Now if I were to look at the value at alpha star, and I use the particular function which I obtained in the previous slide, then I simply put it in that function and I get the same value here, 0.2424. So you can see that these two functions represent the same thing. One of them is in a form of vectors, and the second one is in the form of simply the one-dimensional step size variable. So that's something which is very interesting. Now, if you look at the lectures, you will see all the mathematics explained, but what the tutorial is doing here is that it is giving you some numbers so that you can figure out the connection between those theoretical aspects and actual numbers. So now the next question is the same question, which is xk is 1, 2, dk is minus ck, function is x1 square plus 2x2 square. So the problem is the same, but now you have to show that f dash at this particular value is less than 0. So when the step size is 0, the derivative of f is less than 0. This should be valid for the one-dimensional problem. Also, we know about the line search criteria, that is ck plus 1 dot dk is 0. Let us try to see if this is satisfied. So first things first, the simple problem is done first. So we have f here, and then what we do is we differentiate f. So we obtain the f dash value, very simple differentiation. You can see here this becomes minus 68, this becomes 132 into 2, and then I have to see that what is the value of this f dash when I put alpha is 0, and of course what happens is I get minus 68, and this is less than 0. Now this is important because what it is telling us is that the function f here, this is decreasing at the starting point. So we are in a search direction which is a descent direction, and therefore the function value is decreasing, and therefore I can find some value of alpha which is going to cause my function here to decrease. So this is something which is a requirement as far as any one-dimensional search or any optimization method based on direct search is concerned, that the value of f dash at the point where the step size is 0 should be less than 0. Now let's look at the second question, which was looking at the line search termination criteria. Now the line search termination criteria is given by ck plus 1 dot dk. So we have to obtain these two measures. Dk of course is known as negative ck, which is minus 2 minus 8, but we have to calculate ck plus 1. Now remember, c is given by 2x1 4x2. That's simply from the derivatives of f, the partial derivatives of f with respect to x1 and x2. And I also know that xk plus 1 was obtained as this particular vector. So what I do is I find ck plus 1, I simply substitute these values here. So here I'm going to get 2 into the x1 value here, and then 4 into the x2 value here. So I get this as ck plus 1 vector. So I now get the dot product of ck plus 1 and dk. That gives me the dot product of these two, and this actually comes out to a small number, but not completely 0, but it is a small enough number, and maybe we can be satisfied with that if we are normal people who are interested in engineering type of solutions. But I'm going to check it out further in the next slide to see if we can get a clear 0 here if we do not do all this round off which we have done, because we have essentially rounded this series to 5 decimal places. This would have gone on and on in some cases. So that's something we will take a look at. So if I was to do that, instead of taking the alpha star value as 0.25757, I take it as 17 by 66. So that's what I've done here. Then I would have got xk plus 1 is half plus 17 by 66 minus 2 and minus 8. Remember, this is dk, this is xk, and this is the value which is optimal step size. But instead of using this decimal up to 5 places, I am using 17 by 66. So I can then do this calculation here. I can write this as 1 minus 34 by 66 and 2 minus 136 by 66 by simply doing some multiplications here, and then I get this value here. Now what I can then do is I can calculate the ck at the value corresponding to this xk plus 1. So ck will simply become twice of this x1 and 4 times this x2 here. So that gives me these two values for the vector ck plus 1. Now of course I have dk is minus ck is minus 2 and 8, and then I can calculate ck plus 1 dot dk, which would give me the dot product of these two vectors. Now if we find the dot product, we'll see it would be minus 2 into this 64 by 66 minus 8 into minus 16 by 66. Now if you look at this multiplication, the second part is going to become positive, the first part is going to be negative. And you can see that 8 into 16 is going to be equal to 2 into 64. So what's going to happen is that this is going to exactly become 0. So in this case there is no round off. We have not taken off any of these particular numbers and truncated it. So that's going to give me the exact line search criteria. Now there is a kind of lesson here. If you are looking at the line search criteria, it is sometime not going to be exactly equal to 0 if you implement this thing on a computer. So what's going to happen, you may have to use some kind of norm here, and you have to say that the norm of this particular value is less than some small number. You can set the small number as 10 to the power minus 3 or 10 to the power minus 6, and then you can check if the line search criteria is satisfied. But if you were to do things purely mathematically, if you were to retain all the decimal places, then it would come out well for problems in general. But what happens is that most of the computers will give you precision to certain number of decimal places, and therefore you have to take recourse to some of these approaches. So in today's lecture we have covered several things, but we have not yet proved the descent direction. So we are going to take a look at that. So we see that the design vector for this problem was 1 2, and the search direction was minus 2 8 coming from the steepest descent search direction. So let's see if this search direction satisfies the descent condition for this particular function. So again, to do that, I have to show that ck dot dk is less than 0. That's the descent condition. If this is satisfied, then the optimization algorithm is going to proceed in a path where f of x is going to decrease. So immediately we have c for this function, which we have calculated several times before. And so I can get ck dot dk. That's going to give me this particular dot product. So remember, c is going to be 2x1 4x2, so I substitute 1 and 2 in place of x1 and x2. I get this value for ck. Tk is of course minus 2 minus 8. We are using the steepest descent search direction, so it's simply the negative of the gradient vector. So I get 2 8, I get minus 2 minus 8. I expand this out as the dot product and I get negative 4 minus 64, which gives me ck dot dk is minus 68. So this is certainly something which satisfies ck dot dk is less than 0. It's negative 68. So I can see that this particular method satisfies the descent condition here. Now, of course, this satisfies it generally also, because if I was to take dk is minus ck, I can see that minus ck dot ck would be negative. So that's of course something which is there, but you can see numerically also that is being satisfied here. So this is the very important descent condition which we need to check anytime some optimization algorithm is being proposed by somebody. So today's tutorial lecture we learned several things. We learned about the importance of the search direction. This is the main thing in optimization as far as many methods are concerned, is the search for search direction. We also saw that the descent condition has to be satisfied. So if somebody is proposing an optimization algorithm and he or she is proposing some particular mathematical expression we can use for the vector dk, then that should always satisfy the descent condition if we are going to consider it for optimization or function minimization. Also, we learned about one-dimensional search or line search. So once you have selected the value of dk, once you have selected the value of xk, then the problem becomes the problem of finding the step size. And finding the step size is a very important problem which we are going to look at the next several videos, and we are going to look at methods such as the golden section method, the quadratic interval method, and so on. So you can take a look at some of those lecture videos also, so that you can follow some of the tutorials I'm going to make on that subject. We also looked at the line search termination criteria, which is something which is used by many algorithms, or at least you can look at in the derivations of many algorithms. For example, when you look at conjugate gradient methods, check out the videos on that subject. You will find that at different points, the line search termination criteria is used in the derivation, particularly if you look at the Fletcher-Reeves method and some of the different conjugate gradient methods. Again, study optimization lecture 6, direct search, and that will then help you figure out things in the tutorial, and of course the tutorial is going to help you figure out things in the lecture video. Make it a point to look at the optimization playlist, and if you feel you need some more training in mathematics, you need to increase your knowledge of math, look at my Math Mania playlist, which contains the solution of a huge number of problems in mathematics, which is certainly going to help you improve your math. And I will see you in a video sometime soon. See you then.